Professor Egger was saying this is a guest speaker next Monday, so it's Monday, right?
Yeah.
Yeah. Maybe I'll come in for that. Sounds interesting. Right, so we're going to go back to this now, okay? Everyone ready? Okay, so in our last lecture, we were going over numerical optimization methods, and we were talking about searching multi-dimensional hyperspaces that you can't imagine. We simplified that so we could talk about it to 2 dimensions, and we talked about gradient methods for finding optimum points, either minimums or maximums. Probably because we're dealing with constrained problems, it's a local minimum or maximum. And we looked at this chart here. You guys remember this? Some of you, this is right towards the end of class. I went over it real quickly. The mathematics behind this is a little bit abstract, but you have this thing called a gradient. A gradient will point to the maximum uphill of a function, right? So you pick a search direction in this hyper. First, you pick a point at random somewhere in the design space, and then you pick you find the gradient at that point. You take the negative of that gradient. Okay, that gives you the search direction, and then you pick a step length. So how far you're going to go until you calculate out the value of the objective function again. Okay, then you do at that point you decide whether you've gotten worse or better. In other words, you've gotten closer to a maximum or minimum, and then you calculate out the gradient at that point, and you pick the opposite direction, and so on until you converge to a point where you stop getting lower and lower values, or you start going up again, or vice versa if you're finding a maximum. And we also discussed that the real software programs actually will use multiple points in a design space and search from those different directions. And there's a calculation about all these points converging? Are they all finding the same point as a local maximum or local minimum? Okay, so you guys remember this? Okay. There's other ways to search a design space that aren't gradient approaches. We're going to talk about 2 methods here, not in real detail because I want to get on to discussing some other things that were part of the lecture today. This is still from last week. And one search method is called the genetic search algorithm. And this search method is kind of new. I think it was developed in the 60s, although I think the first application to light weighting was in the 90s, 1990. But this is a method that mimics evolution of animals and people and things. So it's kind of a biomimetic method of finding your local minimum or local maximum. It says you have a population of design solutions. Okay, so a design solution would be somewhere in that hyperspace, that design hyperspace. And the fitness of each of those solutions is judged. In the case of light weighting, it's going to be what is the weight of the solution? Is it a heavy solution or a light solution? The solutions that look like they're lightweight or going towards light weighting will be, I don't know, for lack of a better term, bred, reproduced, okay? And then you'll get some offspring. The offspring are created from the parents using this method called crossover and mutation. So you pick up, I should say that the population is defined by genes, kind of like we talk about when we talk about animals and humans. And the string of those genes is called a chromosome, just like you talk about with an organic person, species, whatever. And then you have a population, which are these different combinations of chromosomes. So the way that you get offspring is you first do what's called crossover, where you take the chromosome and you pick a line in a position, maybe halfway in between, and then you trade up and down between the different genes, okay? And then you have some stochasticity built in the model that will do what's called mutation. So you'll take at random or quasi-random some points, some of the genes, and you'll switch them. The way I've shown this here is that we're doing this in a binary way. It's zeros and ones. That's the gene is either a 0 or it's a 1, but it doesn't have to be. There's some algorithms that will use, whatever, 1 through 5, 1 through 10, 1 through 100. Anyway, so once the offspring are created, then that becomes the new generation, the new population. Those population are weighted for fitness. Did things get lighter? Did they get heavier? Or did you get closer to a maximum or closer towards a minimum? Okay, and then the process begins again. And this loops iteratively, so many times until you begin to get to a solution where either everyone looks alike or your objective function isn't getting any higher or any lower, depending on if you're looking for a maximum or a minimum. And this guy, Professor Haleva, and we can say this better? Haleva? Okay. I've got this paper at home, but I've never met the guy. Anyway, so he was, I think, the first person to apply this type of light weighting, or this type of search algorithm to the light weighting problem. And he used a much more complex example than what I just showed you. He used these chromosomes that were maybe 30 digits long, so much more complex. And he seeded the design space with several parents, a huge population, and then begin that same algorithm again, and then used minimum weight as the fitness. So the lowest weight parent or the lowest weight member of the population was considered the fittest, and then those are the parts of the population that were bred, so to speak, and create offspring. Okay, those offspring were put through this mutation process as well to introduce some stochasticity into the problem, and then those were judged for being the lightest weight solution, so the fittest. So this is, again, an iterative approach. The interesting thing is the way he took into account the constraints. So remember last time we talked about constraints, and that, for example, if you had a tube or something, it couldn't be below a certain diameter. That might be a constraint. This approach used here was that if it was outside a constraint, there would be a penalty function. So something that might have been lightweight, if it was outside the constraint, would get a weight penalty put onto it, which would make it heavier, which would make it look less fit. Okay, so that's how this guy dealt with that problem of the breaking constraints. Okay, another algorithm. Yeah.
The genetic mutation, have any benefits? Why would I use that versus the cells?
So I'm not. Well, I'll talk in a couple slides here about the relative use of each of these different methods. But I'll say that from what I've read is that if you don't have the mutation in there, what happens after time is that the offspring begin to look too much like their parents, and it's sort of like inbreeding. Okay, so the mutation is put in there because it actually, I don't know that I can explain why, but it introduces a factor of stochasticity in there, which results in ultimately better solutions. How's that for an answer? Okay. All right. Okay. Particle swarm is another search algorithm that some people have used out there. This is a search algorithm that's meant to actually mimic a swarm of bees. Okay. So a swarm of bees looking for honey. I guess the honey is at the optimum, the minimum or the maximum. So this is actually, I think someone in this room, I can't remember who it was saying that this search method, particle swarm and genetic, are really conceptually the same thing. But I don't know that I agree. I think there's some small differences here. The idea with particle swarm is that you have this design space. You seed this design space with a number of solutions. You spread out those solutions homogeneously over the design space, and then you begin to calculate out the objective function for each of those points. Right? The objective function is used to calculate out a search direction. Okay. I shouldn't say that. There's this distribution of particles. Each particle has a vector associated with it. The vector points in some direction that's initially the direction. This search direction is initially pointing in some direction that's chosen randomly. Okay? The particle is moved to that next point based on that random design vector, and then the objective function is recalculated to see if you see who went up and who went down. Depending on if it's a maximum or minimum, that's either good or bad, right? And then for the ones that were good, so the design vectors that led towards a direction that was maximizing or minimum, depending on what your goal was, the next set of design vector, the next set of search vectors, is changed to again point in a direction that would be consistent with going towards that maximum or minimum. And then you iterate through these different design vectors until I guess all the particles begin to go to one place where you find the local max or local minimum. Okay, any questions on this one? We got a lot to cover today, so I don't want to spend too long on this sort of stuff. Honestly, from my experience, I've used the gradient method more than any of these other ones. That one seems to be the most I don't know, reliable from my experience. But I did include this table here that talks about the different methods and how they compare. In general, the genetic approach and the particle swarm approach are better at finding global maximum and minimum because you're seeding in so many different areas. They also tend to be less. They tend to be more computational, right? You have to use a lot more calculations to figure out where all these different particles or different populations are going. Whereas with the gradient approach, I know I mentioned that you'll search from several different directions, but usually the number that you search from is nowhere near the number of bees or parents that you would use in the other two methods. Anyway, so the time to converge is better with gradient approaches, and like I said, from the software that I've used, it seems to be more popular as well.
Aren't the genetic and particle swarm methods better partially because they have multi-start? So can't you do multi-start gradient methods and get kind of the same effect and make them better at finding global options?
You could. It's all a question of how much computation power you have, right? Because yeah, you could use the gradient method, and you'd start with a homogeneous distribution of points solutions all over your design space, just like you do with particle swarm or genetic, and you could use the gradient method on all of those, right? And you could do the same thing, but it's a lot more computer intensive. And if you're, it comes down to how big is your design space, right? We've only really looked at two-dimensional design spaces here because that's all I can think in terms of. I don't know about you guys, but I can't really think in terms of more than two. But clearly in the real world, there's design spaces that are much larger than that, right? There's millions of variables, and we'll get to that a couple slides away. When you're looking at millions of variables, sometimes genetic, with today's computer power, sometimes genetic is, or sometimes gradient is the only thing you can use. Moore's law. Just want to point this out, as this shouldn't be any surprise, but as computers have gotten faster and memories become cheaper, the number of variables, the number of design, the size of the design space has only increased as you have cheaper processing power and cheaper memory. And I just wanted to show this graph to show that those two factors track each other almost identically. Okay, last part in last week's lecture, Garrett Vander. So I wanted to introduce you to Garrett Vander. He's still alive. He lives in Monterey, California. Lucky guy. And he was kind of a late starter. I guess he almost failed out of high school, but it turned out he was brilliant. He just didn't know it. And he went to University of Arizona, and his talents were recognized by his professors, and he was encouraged to continue learning more about structural analysis. He became, I would say this guy is the world heavyweight champion in search algorithm development. So this guy's written a couple of books. I've got him at home, and he talks about search algorithms and how he's developed these search algorithms. He's the kind of guy who goes into a room and starts fighting with other people about whose search algorithm is better. He started a company called Vander R&D. This is a company that sells a software that allows you to do some of the tools we're going to talk about in a minute, or use some of the tools we're going to talk about in a minute, like topology optimization, topometry optimization, shape optimization. The software is called Genesis, and it has a pretty good GUI, and it has a finite element code incorporated in it. It's very useful. I've used it many times, mainly in the automotive industry. I've used it, and let's see here. It's sort of like, the company is sort of like Honda. So Honda is a car company that they say lives to make power engines, so gas engines, internal combustion engines. They don't really care what they're using them in, but they're just interested in making better motors, right? So Honda makes snowmobiles, they make snowblowers, they make cars, obviously, they make motorcycles, and people say that they really don't care about what they're making as long as they can make a better engine, a better combustion engine, a better motor. This guy's the same way. I don't think he really cares much about topology optimization or any of the tools. What he really cares about is is making more and more efficient, more powerful search algorithms. He's actually the grad student of Lucian Schmidt. So if you remember last week, I introduced another guy. His name was Lucian Schmidt. He was a professor at UCLA when he retired. He was a professor here for about 8 years. And actually, this guy, Garrett, Vander is one of his grad students. So again, the only reason I really bring this up about this guy is that if you want to learn more about search algorithms, you can go to the library right upstairs and you can pull up a bunch of papers from him. And you can read all night long if you want. You can learn a lot more about search algorithms. Okay, so that was lecture 4. Anyone have any questions about search algorithms? No, we're good? Okay. Right, so back to this. Lightweighting, structural efficiency is about materials and geometry. We've been sort of neglecting the material side of this, so I've brought in some samples just to remind people that you can, we've been talking about geometric and mechanical design a lot more recently, but I wanted to bring in some samples of some materials that have been designed. So these look pretty boring. These are just some little metal sheets, okay? We have one that's steel. It's beginning to rust. This is just just a cheap steel. I think it's a 1020 steel. It's just a low carbon steel, nothing fancy. It has a modulus of about 200 MPa. We have an aluminum one. I'm going to pass these around. Okay, exact same size, a little bit thinner. Okay, this is, I think, a 61 aluminum. It's nothing fancy, just a sheet of aluminum. And then we have a piece of aluminum that has Nextel or aluminum oxide fibers embedded in it. And this is a great example of where a material has been designed to be stiffer than its cousin. Okay, so this is aluminum. These are both made out of roughly the same alloy. It wouldn't matter because all aluminum has about the same stiffness anyway, same Young's modulus. But this is like 2 to 3 times stiffer. And what you're going to do is I'm going to send these around the room, and I want you to try to bend them. Don't yield them. Don't like bend them like past the point where they're going to fail, but just flex them a little bit. And I want you to feel how stiff these are. Okay, and you're going to see that when you get to the aluminum, the one that's reinforced with aluminum oxide fibers, it's incredibly stiffer. So I'm going to pass these around and try to keep them in order. And I think, see, this one is steel. It's labeled steel. This one's aluminum. It's labeled aluminum. This one just says 3M ALMMC. It's because the fibers are made by, this actual piece was made by 3M. It's a Nextel fibers and aluminum oxide fibers sold by 3M. So you pass those around and just bend them a little bit. So just feel how stiff they are. Get an idea of what they're doing. So that's steel. That one's a lot thicker. Now pick up the aluminum one. Okay, it's a lot. You see, it's a lot softer. Okay, and then try that one. Significantly stiffer. See that? So here's where we've designed in the stiffness of the material. Okay, I'm going to go back to geometry now. Okay, mechanical design geometry, and we've spoken about beam mechanics, right? We talked about if you have a beam that's under bending or torsion, what the stress distribution in that beam or tube looks like, and how you can design the geometry of that beam or tube to be lighter and stiffer at the same time. We showed some bicycle frames, and we showed that by going to, for example, on a bicycle frame, by going to a larger diameter tube at a thinner wall, you can actually produce a stiffer, lighter bicycle frame. Okay, so you got both of them there. What we haven't talked about is some of the tools that are out there where we can use these search algorithms coupled with finite element analysis to find the optimum geometry of a part. We can let a computer do it instead of trying to figure it out on our own, which sometimes can be impossible. The tools that I'm talking about are called topology optimization, which I've discussed a little bit, which is what this is. Topometry optimization, which we'll get to. Topography optimization, shape optimization, generative design. All these tools rely on finite element analysis. Rely on finite element analysis in order to find the best design. So who in this class has had a course on finite element analysis? Okay, so not that many people. Okay, so what I'm about to go over might be review for those who raised their hands, but I just want to talk a little bit about finite element analysis. And the calculation I'm going to show you is really ugly. It's really complicated, but I don't want you to stress out about understanding it too bad. I just want you to recognize how complicated the calculation is, and then think about how glad you are that you don't have to do it by hand every time, okay? And understand that this is where computers really shine, is that it enables you to, or enables an engineer to do a stress analysis on a very complex geometry and be able to just put it all on the computer and then let the computer take care of it. So let's start here. You have an eraser, let's say. Say that it's some homogeneous material, and you put this in compression, okay, this way. And you can very easily calculate the stress on this if you know the geometry. You know that the stress is going to be equal to the force divided by the cross-sectional area, which in this case is B times H. Pretty simple stuff, right? Okay, you can, if you were working at Boeing or Caterpillar or Polaris or whatever company, and somebody gave you a beam and they said this beam is under a tensile load or it's under compression load, pure tensile, pure compression, it's a homogeneous material, you had a pair of calipers, you can measure the cross-section, you'd very easily be able to calculate out pretty closely what the stress is in that part. Okay, if it was under torsion or bending, I've showed you the equations before, it's still pretty simple, you can go ahead and calculate that. But what happens when you've got a very complicated shape that doesn't have a constant cross-section, like this connecting rod? And you know, you guys, I'm sure a lot of you know how car engines work. Most of you probably. There's a piston, right? The piston has a combustion process on top of it that applies a load to the top of the piston, or a force. The piston goes down. The piston pushes on through a wrist pin, pushes on a connecting rod. The connecting rod turns a crankshaft. That crankshaft turns a shaft, which turns the wheels of your car or your motorcycle or your snowmobile, whatever it is. But suppose you're the design manager on this connecting rod. You know, how do you figure out what the stress is on that connecting rod? Any ideas? When it's a complex loading like that? No? Well, I guess in the 60s, I think, the finite element method was developed. Was it the 60s? That sound right? Yeah. Okay, in the 60s, the finite... 75. Okay. The finite element method is a way to approximate the stress at every x, y, z in the volume of some part with a complex geometry. And it's not perfect. It's not perfect. There are definitely some assumptions made, and I'll show you in the calculation coming up where some of those assumptions are. But it allows you to get pretty close. From my experience, a lot of the mechanical engineers I've worked with tend to, I don't know, maybe put too much trust in this finite element calculation. There's some approximations there they may or may not be aware of, and honestly, in a big company, like the finite element analysis results can become a big political chip. You know, the finite element analysis said it would work. Yeah, I know the car didn't pass. You know, it broke in half, but the finite element analysis was good. So I always want you to. I'm just telling you this because I just want you to remember always that finite element calculations are approximations. They're not fact. Okay, everyone understand that? Okay. Having said that, the way a finite element calculation works is that you take your complex geometry, you draw it up in CAD world. Don't bend it, Paige. Okay. All right. You break it up into little elements. That's called discretizing the volume. And then you can think of each of these little elements that are in, you know, virtual world or in computer land, right? They're sort of like little parallelepipeds or little plates or little beams that can be approximated by a series of springs. Okay? As you go to more complicated elements, the calculation becomes more complex. Connecting these elements from one element to another is a thing called a node. So a node is kind of a theoretical idea, right? It's a theoretical abstraction. It says you've got two elements coming together, and somehow, even though they're their own separate little pieces, they fit together perfectly, and they come together at one point in space, which kind of isn't physically possible, right? So it's sort of an abstraction. Because you have these little elements, these little elements that are made of materials, you can begin to write out equations that would describe how they behave when subject to some type of boundary conditions or a force, some type of boundary conditions that changes their geometry. So here's some calculations right here. So the displacement can be approximated by some approximation m. It's like a shape approximation times the displacement vector d. The strain can be calculated from that displacement vector using what's called the strain displacement matrix B. Okay, once you have a strain, you can multiply it times a stiffness or a stiffness matrix to give you a stress. So there's your net result. You wanted to get to stress. Here's how you get to it. And then there's this thing called the stiffness matrix, which is used in finite element analysis to go from the displacement vector to the stress in your model. And it's given by this equation here, which is an integral over volume times this strain displacement matrix and times the stiffness and over the volume. You integrate over that volume. Okay. So here's a really simple example of a finite element calculation. You have a spring. Okay, you have one spring. It's got a node on the left and right. There's boundary conditions applied to those nodes on the left and right. And then there's this thing called Hooke's law. You guys probably all know that from your first year of physics. Yep, everyone know Hooke's law, right? Hooke's law says that the force equals some k times the displacement x. Correct? Okay, that's all. You guys should all know about that one, right? And through drawing the free body diagram of this spring and the nodes around it, you can come up with the equations shown here, P1 and P2, right? And from that, you can draw you can write out a stiffness matrix K. You can make basically we're just taking those two equations, we're putting them in vector form. We're going to use linear algebra to solve it. In this case, you can't actually solve it, but don't worry about that for now. And you come up with you can calculate out like I said, a stiffness matrix K times a displacement vector X equals a boundary condition vector P. You can transpose the stiffness matrix to get to the displacements X, and then knowing the length of the spring, you can use that displacement and the stiffness to get to a stress. You can all calculate the stress in that sort of spring. Okay, this is a pretty basic example. I'm sure you guys have seen this a zillion times, right? Okay. Now, the next level of complexity would be what happens if you go up a dimension. So instead of having a one-dimensional spring or stiffness element, you have two dimensions, and you've got this triangle, right? You've got three dimensions now, okay? I mean, sorry, you got two dimensions, but you've got three nodes, okay? And now each of these nodes and each of the vertices of this triangle can go in different directions. They have their own degrees of freedom, 3 degrees of freedom per node. I'm sorry, 2 degrees of freedom per node. Okay, and now the calculation becomes a lot more complicated. I don't want to spend a real lot of time on deriving this equation because you guys can look this up if you want, and I think it's probably better we talk about topology optimization. So I'm going to go through this kind of quickly unless you guys really want to see this. No? Okay. No? Okay. All right. So so you have displacements u and v at each of these nodes. That can be the displacements at each of these nodes can be approximated or modeled by some shape function n. That function n can be defined in a zillion different ways. In this case, we use this ABC to define it. That includes a big A in area. You calculate a determinant out based on those little a's and little b's and little c's, and you can come up with an equation that describes this shape displacement, this n shape function. Okay, you can put that into this u equals n times d, so the displacements time equals the shape function n times this d displacement vector. Okay, the strain is equal to these derivatives of u and v as a function of x and y. Okay, that equals to this strain displacement matrix times the vector d. It's then very easy to given the shape equation that we picked for n, it's very easy to go ahead and calculate out the strains in x, y, and xy. They're given right there. It's pretty simple. From that, you can calculate out the strain displacement vector or a matrix, which then gives you k. K is the stiffness matrix. You can then calculate like I said, you can calculate the stiffness matrix. You can use the boundary conditions with this displacement, or you can use the boundary conditions with this stiffness matrix to calculate the stress. That's pretty much how finite element calculations work. Okay, this is complicated stuff. So I've just shown you 3 pages of calculations for a 2D element. The real world doesn't use 2D elements very much because the real world is much more complicated. We use, 3 or 3D elements, and they may have 4 nodes or more depending on the shape. And so this calculation gets really ugly really quick. It gets pretty difficult to do by hand. Some sadistic professors will probably make you do this at some point in your life to calculate out all these equations for a 3D element. I just want you to know about this, that there's this approximation n in there. Okay, the shape function n. It's an approximation. It's an approximation. It's an approximation, which means that the stresses that you get are also an approximation. So when your VP goes to his boss and says, "Hey, the finite element calculation said it wouldn't break," remember this. There's an approximation in there. Okay? Everyone understand that? The other thing I want you to remember is that these calculations are big, ugly, and complicated. They're best left to a computer and somebody who had the patience to write the code to solve these things. But be respectful. Know that this is complicated. It's there. That's all you really have to know, okay? Okay, so let's talk about something that's more interesting. Let's talk about, to me at least, let's talk about load paths and load path optimization, so-called topology optimization. Suppose you had this column, another column, and it's subject to 2 forces F, which are equal and opposite. This thing is under compression, right? Okay, so that's a pretty direct load path. There's 2 forces, there's something in between it. It's a really direct load path. Now, some people might try to solve that problem using the shape we see here on my left, which is much more complicated. See, now you've got, rather than just having a simple beam under compression, you've got all these beams that are under some combination of bending and compression and tensile. And in order to make the one on the right as stiff as the one, the one on the left as stiff as the one on the right, you'd have to use a lot more material. So which one of these do you think would be heavier, the right or the left? Right, exactly. This one over here would be a lot heavier, right? Because you'd have to put so much material in there to get equal stiffness, okay? Because the load path is all jimmied up. There's, it's indirect, it's dislocated. It's never going to be an efficient lightweight structure. Believe it or not, on most cars we see similar things happening. Here is a body structure off a Mini Cooper, and if you look, there's we talked before about body structures, and we see that there's these rails here, the rail structures. Here's some shock towers. The loads from the suspension feed into these shock towers through the shock and damper package. So the force is up. When you hit a bump, the force goes up. For optimum bending, it's efficient to have the load that's put in the shock towers go through the entire structure, including the roof, to the rear shock towers. That's efficient, right? But in most cars, there's this dislocation. There's the shock tower here, and then there's the A-pillar here, which goes over the roof and down to the C-pillar and to the rear shock tower. But there's this big gap between them. It's not an efficient load path, right? You've got one force here and one force here, and you've got this big thing in between, that's big void in between where there's no structure taking up the load. It's actually very similar to this. There are cars out there that are more efficient. I wrote a paper, actually a book chapter, on this design a couple years ago. And I can show you the book later. You can look it up if you want to read more about it. But the idea is that the shock tower would become part of the base of the A-pillar. So instead of having this dislocated load path, where you've got one load here and then the other load that reacts it over here, you put the two together. That's what I mean by a direct load path, an efficient load path. Make sense? So there's this great tool called topology optimization. If you have a very complicated structure, maybe you've got an airplane with wings and a bunch of people sitting inside it, or you've got some type of tractor or backhoe or something that has loads coming from all different directions. It's very complex. As a human, it's difficult to intuitively always know what are the best load paths through that volume where you can put structure. Sometimes it's not easy to know where to put the load paths in order to get the most efficient structure. This guy, Benzoa, who's from Denmark, and Kikuchi, they wrote this paper in '88 about what we call today topology optimization. They started off with some kind of random structure like you see here, and they put on the structure some kind of random boundary conditions of different tractions and different forces in different directions, different constraints, okay? And then what they did is they used, effectively, they used finite element analysis to discretize this random looking structure into a bunch of elements, okay? And then what they do is they say the density of each of these elements can go between being fully dense, which is a 1, or have no density, which is a 0. Okay? Then what they do is they say, if I want the most efficient load paths through this guy, I'm going to calculate the aggregate strain energy for all these elements, and I'm going to search the design space of these elements where density is the design variable, and I'm going to figure out where I get the lowest strain energy. So let me repeat that again. You've got this crazy random shape. Okay, you're discretizing this into elements. Suppose I drew that better, right? And each of these elements is designed a density, is assigned a density. That density is now the design variable. The density can go between 0 and 1. So you're initially assigning a density to each of these elements, right? Suppose you've got 500 elements. What's your design space? How big is your design space? Page, you have it. 500, exactly. So you've got 500 variables now. And then what you're going to do is you're going to put a constraint on the amount of material you have to distribute to each of these elements. Okay? So you can't have the initial weight. You have to have a lesser weight. And you're going to figure out what is the most efficient way to distribute these density, this mass, in order to get a structure that has the lowest aggregate strain energy. Now, strain energy has a K in it, a stiffness in it. So somehow I have to figure out the K. And part of the genius of this paper that these guys worked on is that they came up with an approach called a homogenization approach, where they relate the density to the stiffness of that matrix, of that element, so a stiffness matrix. Okay, so the stiffness matrix and the density go together, as well as a mass. So here's a simple example. We've got our beam again that's under compression. And let's say we break this up into 3 elements. The design volume is what's shown here in the dashed line. That's the space you have in order to put structure. You've got a limited amount of space to put structure. You can't put it everywhere. Okay? And the variable is going to be row 1, row 2, row 3. So these are the densities of each of those 3 elements. So your design space is how big? 3, right? You've got 3 variables. Row 1, row 2, row 3. Those are your design variables. And so that's your design space right there. Using this homogenization approach, which is very complicated, I'm not going to go over here, you can then relate the density of each of those elements to a stiffness matrix, K, and a mass, M. Then you can very easily calculate out the strain energy, the aggregate strain energy. So you use finite element analysis to figure out what the strain is on each element. And then you can calculate a stiffness matrix. Then you can add up this. You can calculate the strain energy for each of those elements. And then you can add all those up and get an aggregate strain energy for the whole system. When you start placing density, you start placing mass, you start tweaking those row variables, right, between 0 and 1. You're going to distribute it so that you get the lowest aggregate strain energy. I'll give you a better example than this. Here you've got a simple beam under cantilever, subject to load P. This cantilever can be discretized. Okay, we know the stress contours. We can look it up in a book because this is well known. I think this was probably figured out in the 1700s. But you know there's some stress field in this cantilever beam. I just drew it here just because I happen to know what it is from looking up in a book long ago. Now you can take this same cantilever beam and you can break it up into, let's say, 500 elements. You then can assign a density to each of these 500 elements. So you got a 500 dimensional design space right here. Right? The design variable is rho. It can be anywhere between 0 and 1. Using the homogenization approach, you can then calculate out a stiffness matrix for each of these elements and a mass. Then you can, using finite element analysis, knowing the boundary conditions, you can calculate out a strain energy for each of these elements. And then you can add up all those strain energies to calculate out the aggregate strain energy for this entire cantilever beam. When you start tweaking, when you put a constraint on the amount of mass you have, so to place in each of those elements, that is, what is the rho going to be? Is it going to be somewhere between 0 and 1? At that point, after doing the finite element calculation, you can begin seeing that the strain energy of the entire system is changing. When you find the point where the strain energy has gone to the minimum, that's the point where you're going to have the stiffest, lightest design. The optimizer has chosen the most efficient load paths for you. It's pretty powerful. Think about that. Okay? So again, you have in this case, you had a 500 dimensional design space. Nothing that I can imagine, and probably nothing that many of you can imagine. Right? Design variable is density, rho. It's going to be somewhere between 0 and 1. The optimizer will search through that design space of 500 different rho values, density values, determine which combination of different rows throughout that structure is the most efficient place to put mass. Once it's figured that out, it'll show you the shape, the most efficient places to put the load path. And for that cantilever beam, it looks something like this. Now, this is very easily scaled up when you've got powerful computers. You can go from 500 elements to 2.3 million elements. So this what you're seeing right here, this is a body structure of a SUV. This is a project I was responsible for at Chrysler. We were trying to find a process to minimize the weight of body structures. We were given this design envelope for an SUV. This came from one of the styling studios. And then this packaging volume, as we call it, is the total volume of places where you can put structure, okay, legitimate places to put structure to make the structure as stiff as possible. You can't put a load path through somebody's head. You can't usually put a load path through the engine, right? So that's why this is very important. This is the domain of places where you can put structural members. We spoke a little bit in a previous lecture about loading conditions, that there are loading conditions that the automotive industry puts on car bodies. They simulate for front impact. They simulate for side impact. They simulate for rear impact. They also simulate for torsion. So how stiff is the body in torsion, because that affects handling a lot. How stiff is the body in bending, because that can affect ride quality a lot. There's in this study, we used about 9 different loading conditions. And we came up with this topology result right here. So again, we had this packaging space, this packaging volume where we could put load. Only where you can put load. You can't put load through somebody's head. You can't put load through somebody's legs. You can't put load through the engine typically. Okay, so we took this volume that we had. We broke it down into 2.3 million variables, 2.3 million elements. Each of these elements was assigned a density. So how big is our design space? Someone yell it out. 2.3 million. That's how big the design space is, 2.3 million. The optimizer that we used then went through and tried different values of these densities for each of the elements between 0 and 1, subject to the constraint that we don't have the same amount of mass as we did originally, and then went ahead and strategically placed mass in appropriate places so that the aggregate strain energy of all the elements in that volume would be minimized. This is a 2.3 million element design space. And we had an optimizer that searched that design space to come up with this. This guy right here, this was going to be the super duper new Camry fighter that Chrysler was going to design and fight with. This turned into the Chrysler 200. eventually. But I stole this from Chrysler about 2 days before I left. And you're welcome to come up here and take a look at this. But this is a 3D printed model of a topology optimization result given those 9 loading conditions. And some of the loading conditions, some of the load paths that the optimizer chose are not so intuitive. Not so intuitive. And that's, I think, the most interesting part about this, is that you can't just think your way through this. You can actually benefit and get a lighter solution through using numerical optimization tools and finite element analysis connected together. We're almost out of time, but I just wanted to show you some of these plots we have. I put together. Some of these topology optimization tools will allow you to go in and look at cross sections of the packaging volume after you've done the optimization, and it'll show you exactly where it's distributed the mass. The areas in red here are the places where the most mass has been distributed. When you look at something like this, this is pretty complicated. It's hard to wrap your head around this. It's even harder to turn this into sheet metal, a sheet metal design. You can imagine what that's like, right? This makes it a little bit easier. The optimizer will show you more precisely, cross-section by cross-section by cross-section, where it's put the mass, where it thinks where the optimization has dictated the most efficient load paths lie. And then there's a bunch of different cross-sections you can look at. This one here, I think, actually is the one in my hand. Anyway, why don't we stop there, because we're out of time. If you guys want to come up and look at this, I'd be happy to talk about it. Where are the metal sheets, by the way? Oh, they're over. Okay. Anyway, great. So that's it for today. Next week we'll come back and talk about some of the other optimization tools. But I want you to think in terms of design spaces and how amazing this is that these optimizers can search through such large design spaces, and how computers have enabled that. You know, we didn't have that 40 years ago. Thanks.